Hey everyone, welcome to this tutorial on red black trees. My name is Gurnoor Singh and I'm a student of SLE 221. You have already covered AVL trees in this unit. Red black trees are the same idea basically a self-balancing binary search tree, but with a different and arguably more practical approach to keeping things balanced within a tree. By end of this video, you will understand what a red black tree is, the 5 rules that define it, how insertion and deletion work, the time complexity, and how it compares to AVL trees. I've also shared notes in the Teams channel, so check those out after watching this as well. So yeah, let's get into it. If we move into the introduction section and see what are red black trees initially. So basically, a red black tree is a self-balancing binary search tree, just like AVL trees, where every node stores an extra color bit that will be either red or black, as the name suggests, to maintain its self-balancing structure during insertion and deletions with much less complexity. What happens in plain binary search trees, we know that if they're in a sorted order, any insertion or deletion can actually degrade to big O and complexity. And that's why we have these structures like red, black, or AVL that helps to maintain big O log and for search, insert, and delete functions. So yeah, we already know AVL trees, but the difference that these are red black trees have that they solve the same problem, but with few iterations or on insert and delete operations. So yeah, mainly they what they do is basically just follow the 5 core rules that we have to understand, uh, and which are rule one that every node is either red or black, simple enough, and every node carries a color. The second rule is that the root is always black, no matter what. These are the empty nodes at the bottom of the tree sometimes, and they don't hold data, but they count as black for purposes as well. So yeah, basically the root node should be black, and every null node has to be black as well, which is the third rule as well. And moving on to the fourth rule, a red node cannot have a red child as well. That's the fourth rule as well. You cannot have 2 red nodes in a row on any path, and this is one of the most important rules that will be seen through the insertion process that we will carry out here. Rule 5 is that every path from any node down to its null leaf descendants must pass through the same number of black nodes. So basically, if we are following a node and there are 2 paths from it, that is towards left or right, each of those paths should have the same number of black nodes. And from what all these 5, we can understand that rules 4 and 5 together are actually what actually enforce the balance here. They guarantee that tree height never exceeds 2 times log n, which is what gives us our big O log n operations. And if we move in towards the insertion walkthrough that we will have, uh, now let's basically talk about how insertion works in this case. Inserting into a red black tree has 2 phases. The first phase is that you insert it like a normal binary search tree, whichever element you want to insert. And afterwards, what we do is after has happened, we fix any of the violations that occur due to that insertion. So the step one is that insert the new node exactly like you would in a regular binary search tree. Smaller values go left, larger values go right. Then step two is basically color the new node red. We always start new nodes as red because adding a red node doesn't immediately break rule 5. It doesn't change the black height of any path. So just for safety. Uh, Afterwards, now what we do is basically check if any rules are violated. The only violation that can happen is rule 4, a red node with a red node parent. Basically red collision. And we fix this using one of the 2 strategies. The first one is recoloring and the second is rotations. So yeah, and what we do make sure by doing all of this is that the root is black at the end as well. The root node should never be red. And if we walk through the 3 cases that we go through when we are inserting into elements or fixing the violations, the first case is that the uncle is red. What it basically means is that if we have, I think it will be better displayed through I'll just move into the screen there in this case, and I'll change the, yeah, share and I'll demonstration. Here in this case, actually, we can see that when inserting towards element, what we do is basically when we insert the new node with color red, here, that is 10, uh, there are no changes. Since it's the root node, it should be black, by the way. And when we keep inserting as we go, as you guys can see, we inserted the new element many here. It was a black-red combination, so no rule violation was there. But as soon as we inserted another element that was red, uh, there's a red-red conflict, basically a rule violation here. And then we basically have two cases. The first is that the uncle node, basically what it means, the adjacent node of the, so basically the node that will be adjacent to 10 here, basically left child of 10, which is left doesn't have a left child here. But yeah, in case it did had a left child, or uh, if it's black, what will happen is that we will do rotation and then recoloring. And within recoloring, what will happen is that we'll swap the color of parent and grandparent. The other case is that if basically if this whole uh, tree was left aligned and we had adjacent child on the right side, which was red, what we would do is basically recolor the parent and uncle, this basically adjacent child node, as black, and the grandparent, basically the root in this case, would be then recolor to red. And if I have to uh, basically demonstrate it, you can see that in this case, what happens is that uh, the uncle, or basically adjacent child, is not here. It's so yeah, since it's not here, we'll just count its value as null, and we'll basically do a rotation and recoloring. And that's what we did. We basically followed a left rotation here, and afterwards, after the left rotation was done, we swapped the color of the parent and grandparent nodes. So it was black, and so 10 was basically black, and 30 was and 20 was red. And once we did the rotation, the colors were swapped. And so yeah, this is basically how we sort of follow the rules. And was the case one uh, while doing insertion. And if we move forward from here, I'll just jump back to the slides here and show you the second case. Yeah, basically, sorry. Yeah. So the other case that we were discussing here is basically if the adjacent uncle is red. In that case, what will happen is basically if you move towards the next. So yeah, here in this case, when we inserting 15 into this uh, tree here, we can see that it was inserted through a proper binary search process, and it went as right child of 10, but there was a red-red conflict here as well. And in this case, the uncle, basically adjacent right child here, is red. And so what we'll do is basically recolor the parent and uncle as black and grandparent as red. So in this case, the uncle here, which is 30, is repainted as black. Parent is converted from red to black. And basically, in this case, the grandparent, the root node, was actually should have been converted to a red node. But basically, since we do follow the first core rule, that is that the root has also, always has to be black. That's why we have kept it black and not changed to red. So these are the basically main cases that are being followed when we are doing insertion in binary trees through red black tree process, and that's what being followed throughout this tree as well. As you guys can see, when we inserted 12 as well, case one was followed, because in this case there was a red conflict, and the adjacent node here, which is uncle, is red, so case one. And so these are the rules that we follow. And if I just jump back to the slides there. So yeah, this was how was insertion being taken. If the uncle is basically red, we just move towards the recoloring process. If the adjacent uncle is black and or not present in that case, we are moving towards rotation and recoloring process. And likewise, if I just move towards the deletion overview here, deletion is a bit more complex than that because overall idea is same, that we delete first, then fix the violations, but it does get a little bit tedious. The process basically that we follow is that we delete the node using standard binary search deletion method. And the key insight in that case is that if deleted node was read, there's no need to do anything else. We are done here. No violations occur because black height of all paths stays the same. But if deleted node was black, that path now has fewer black node, which violates a rule 5, and we call this a double black situation. So we follow the step 3 in that case, and that is we fix the double black using 4 cases, all based on what color the sibling node is. So if case 1 basically is if the sibling is red, we rotate the parent towards the double black side and swap colors of parent and sibling. This sets you up for another of the next cases. And I'll just show that as well. So here in this case, so yeah. So if the sibling is red, we rotate the parent towards double black node and swap colors of parent and sibling. And if the sibling is black and both siblings children are black, we follow the process of recolor the sibling to red, move double black problem up to the parent. If parent was red, make it black. If parent is black, repeat from the top. And then we have another two cases here, sorry, which is that if the sibling is black, uh, what happens is that sibling far child is black, near child red, and we basically rotate the sibling away from double black node and swap the colors of sibling as near child, which makes it case 4. And what case 4 essentially is that sibling is black and sibling is a far child of red. And in that case, what we do is basically rotate the parent towards double black node, swap colors of parent and sibling, and color the siblings far back to the right child. And this is basically how double black is resolved. And if I have to demonstrate it through this binary search tree from which I deleted the elements here, we can see that this is the binary search tree that we have. And from here, if let's say I want to delete 100. Now 100 in this case is basically a red node. And if I delete it, the basically the black length of the tree remains the same. The structure remains the same, as you can see. If from root I have to go towards the null, I can take these values after deletion and say, okay, it was one black node, one black node, one black node, and one black node. So the black length of the tree didn't change. That's why we don't need to do a lot here. But in that case, let's say if I have to delete 110, in that case, I look towards the adjacent sibling as well, which was black again. And if I delete upon 110, basically here 120 will take its place. So that's not an issue. And the black print remains the same. But if I have to delete 80 in this case, which is a black node, uh, in order to replace 80, there will be null values, which automatically we know that we do recognize null values as black in red black trees. But what will happen is basically that the black length of the tree will reduce and it will become unbalanced, calling a double black issue. And we will basically recolor in order to solve it. And here in this case, what I did was basically, I think, followed the cases that was presented earlier. And here in this case, the adjacent sibling was 120, which is black. So all that was required was basically recoloring. And so, yeah, the red color node was changed to black and black was changed to red. And yeah, that's it. And afterwards, I think 120 deletion had no change because it was red. And yeah. But again, if I followed another case here, which was deleting 90, which was again a black node, it again caused a double black situation here. In order to solve it, then I had to follow a rotation process and then recolor the whole tree again in order to balance it. So yeah, I basically gave a quick overview of deletion because it's much more of a complex process, but if followed correctly, it can be very helpful. And moving forward towards the whole explanation of this as well, the complexity, which is one of the main reasons that we use this, red black trees as well. Uh, Now, search, insert, and delete are all big O log n. And in the best, average, and worst case, and the reason for this comes directly from the rules we just covered. Rules 4 and 5 together guarantee that the height of the tree can never exceed 2 times log n plus 1. Even in the absolute worst case, the longest path from root to a leaf is at most twice the shortest path. This means that no matter how many elements you insert or delete, every operation visits at most that many nodes, giving you a guaranteed big O log n bound every single time. And space complexity in this case is big O n, which is one node per element plus the color bit. Uh, with that being said, if I have to differentiate between or basically compare red, black, and AVL trees, what we can see from this whole presentation is that both are self-balancing binary search trees and both give us big O log n for all operations. The difference is in how they balance. AVL trees are more strictly balanced. The height difference between left and right subtree can never exceed 1. This makes AVL trees faster for searching because tree is shorter. Red black trees, on the other hand, are less strictly balanced. They allow it a bit more height, but compensate by doing fewer rotations during insertion and deletion. This makes red black trees faster for write heavy operations. If I have to tell you about this in practice, the Linux kernel that are created, they use red black trees. Java stream app uses red black trees, and most standard library implementations as well, because real world applications tend to have more writing sections rather than reading. And if you're building something read heavy like a database index or something else, AVL might be a better choice. And if I have to wrap up the whole thing, I'll say that a red black tree is a self-balancing BST that follows 5 rules, and every node is either red or black. The root is black, null leaves are black, no two consecutive red nodes are allowed, and equal black height of on all paths is required. Insertion starts always red and fixes violations using recolouring and rotations across 3 cases. Deletion is only problematic when a black node is removed. So creating a double black situation is fixed across 4 cases. And yeah, apart from that, uh, if we are comparing this to AVL trees, red black trees are better for basically write heavy systems, while AVL trees shine in read heavy ones. And yeah, I've dropped the notes and cheat sheet in the channel as well. And so yeah, this was the whole presentation. Thank you.